Dilute Solutions Colligative Properties Part 5, presented by G. Satyanarayana Gaud, Assistant Professor, Dr. B.R.R. Government College, Jadcherla. In last class, we have discussed about the concept of elevation of boiling point, and we have derived the relationship between the elevation of boiling point and molecular weight of solute from the concepts of thermodynamics. So now we see the relation between elevation of boiling point and LVP. LVP means lowering of vapor pressure. What is the meaning of lowering of vapor pressure? It is the difference between the vapor pressure of a solvent and vapor pressure of solution in which non-volatile solute is dissolved at same temperature. That is called lowering of vapor pressure. Elevation of boiling point, once again let you see what is elevation of boiling point. It is the difference between the boiling point of solvent, boiling point of solution and boiling point of solvent. The boiling point of solution is greater than the boiling point of solvent because the vapor pressure of solution is less than the vapor pressure of solvent. So now we see the relationship between the elevation of boiling point and the lowering of vapor pressure. This graph is given for or drawn between vapor pressure of the solution and versus temperature, vapor pressure and temperature. Okay, next in this we have taken three different systems. One is a solvent. This line indicates a curve of solvent. This indicates a curve of solvent. You see, as the temperature increases, vapor pressure of the solvent gradually increases exponentially. And finally, it becomes equal to the external pressure. This is the external pressure, means it is 1 bar or let's say 1 atmosphere. So the boiling point of a solvent is T naught. Now in this solvent, same solvent at same temperature, we have dissolved some non-volatile solutes, a specific amount of non-volatile solute to form a solution, homogeneous solution. We know that the vapor pressure of solution is less than the vapor pressure of solvent. So we see the curve of the solution lies below the vapor pressure curve of solvent. So for solution 1, this is the curve. As the temperature increases, the vapor pressure of that solution also increases. Finally, it becomes equal to external pressure here. So what is the boiling point of this solution 1? T1 is the boiling point of solution. Clearly, we can observe here T1 is greater than T naught. The boiling point of solution 1 is greater than the boiling point of solvent. This difference is called as this difference. Now this difference is called as delta TB, elevation of boiling point of solution 1. Okay. Next, we have prepared another solution. It is more concentrated than solution 1. Means it has more quantity of non-volatile solute compared to solution 1. So its vapor pressure further decreases. As the temperature increases, the vapor pressure of that solution 2 gradually increases, finally becomes equal to external pressure at C point. You can see that. Now the boiling point of the second solution will be T2. So the difference between this T1 and T2, this difference is called delta TB of second solution. So at any temperature you can, so now you see at point A you can clearly observe this is the vapor pressure of solvent, this is the vapor pressure of solution 1. You can see P1, vapor pressure of solvent is P naught, and this is the vapor pressure of solution 2, it is represented by P2. And we can see that P naught is greater than P1 is greater than P2. What is the relation between these boiling points? T2 is greater than T1 is greater than T naught. That we can observe clearly with help of this graph. So in this we can see similar triangles. What are the similar triangles you see? One is ABD. This is the first triangle. A part of the straight line, a part of the curve is approximately treated as a straight line or taken as a straight line. The second one is ACE, is it? This one, ACE. this one. So ABD and ACE are similar triangles. According to the properties of similar triangles, we can write it as the ratio between the similar or identical sides will be constant. That's why we can write AB divided by this one, AB divided by AB divided by AB divided by AC is equal to, is it AD divided by AE, this one. Okay, so what we are writing, you see, one is AB divided by AC is equal to AD divided by AE. So you can substitute these values from the graph. From graph, you can substitute. What is AB? AB is T1 minus T0. This AB is nothing but, this AB is nothing but what? T1 minus T0. So T1 minus T0 we have substituted. Similarly, you see AC. AC means this AC, A to C, AC. It is nothing but T2 minus T0. So we are writing T2 minus T0. That is equal to what is AD? AD is this difference. It is nothing but P0 minus P1. We are substituting it. Now AE is, this AE is P0 minus P2. You can substitute. So T1 minus T0 is delta T1, means elevation of boiling point of first solution. T2 minus T0 is the delta T2. It is elevation of boiling point for second solution. And similarly, you can see this P0 minus P1 is LVP, lowering of vapor pressure of first solution. P0 minus P2 is the lowering of vapor pressure of second solution. So from this, what we observe, delta T1 by delta T2 is equal to delta P1 by delta P2. Okay. So this is possible when, so based on this, we can write delta T is directly proportional to delta P. Means the elevation of boiling point is directly proportional to lowering of vapor pressure. That we can clearly understand from this graph. Delta T is directly proportional to delta P. Next, we will derive the relation but from this relation, that is delta T directly proportional to delta P. We will derive the relation between elevation of boiling point and molecular weight of solute. You see here. So delta T is directly proportional to delta P we are writing. And also we can write delta P by P naught. Why? Because here proportionality constant is there. Sorry, proportionality symbol is there. In the proportionality symbol is there and P naught is a constant. When delta T is directly proportional to delta P, delta T also directly proportional to delta P by P naught, because here the P naught is a constant. So we can add that P naught here. We can write the P naught there. But what is delta P by P naught? This is relative lowering of vapor pressure. The relative lowering of vapor pressure will be equal to mole fraction of solute. What is the mole fraction of solute? It is X2. In case of dilute solution, X2 can be written as N2 divided by N1. Correct or not? We can write N2 divided by N1. N2 means number of moles of solute divided by N1 means number of moles of solvent. So the solute is given or represented with small letters, whereas the solvent is given represented with capital letters. Means small w by small m. This part, it is N1 divided by capital W by capital M. It is N2. Here once again, please. Small w by small m, it is N2, whereas capital W by capital M is N1. So generally we represent 1 for solvent and 2 for solute. So small w by small m into capital M by capital W. Small w is the weight of solute in grams. Small m is the molecular weight of solute. Capital M, molecular weight of solvent. Capital W, weight of solvent. All these are in grams. So therefore, from these equations, means equation number 1 and 2, let's say for example here it is it. Equation number 1 and 2, what we can write it is, see, delta T is directly proportional to, this can be related now, small w capital M divided by, okay, so small w capital M divided by small m capital W. Or delta T is equal to, instead of proportionality constant, we are writing that 1, is it? Delta T is equal to K into small w small capital M by small m capital B. K is a proportionality constant. Now we want to introduce the term of molality in this. In order to introduce term of the molality in this, now we are dividing this equation by 1000 and multiplying by 1000. That is 1000 by 1000. Multiply by 1000 and divided by 1000. So what is the definition of molality? It is the number of moles of solute dissolved in 1 kilogram of solvent. The formula is small w by small m into 1000 by capital W. This is the weight of the solute. This is the molecular weight of solute. Capital W is the mass of, or the weight of. Mass and weight, both of them are taken as the same concept, sense in chemistry, is it? So capital W is the mass of a solvent in grams. This is the formula for molality. Now you see in this equation, small w, small m, capital W, and 1000. The rounded off all terms represent what? Molality. So instead of these, we can write small m. If you write small m for these, so delta T is equal to, here you can see, delta T is equal to K into m by 1000 into small m. What are the remaining terms? Is K into m divided by 1000 into small m. So this is totally one constant. Km divided by 1000 is a constant. It depends only on the nature of solvent, because capital M is a molecular mass of solvent. So Km by 1000 is now represented by another constant, that is Kb. We represent it by Kb. So when you represent it by Kb, delta Tb becomes equal to Kb. This totally we are replacing it by Kb. So Kb into molality. This is the relation between the molality and elevation of boiling point. You remember, delta Tb is equal to Kb into molality. What is small m molality? What is Kb? It is molar elevation constant, or we call it as ebullioscopic constant. So delta Tb is equal to Kb into molality, or delta Tb is equal to RT square divided by delta H vaporization into capital M1 into small m, because Kb is equal to, already we have seen in the last class, Kb is equal to RT square divided by delta H vaporization into M1. R1 is the universal gas constant, capital T is the boiling point of solvent, delta H vaporization, it is a molar enthalpy of vaporization of that liquid, capital M1 is the molecular weight of solvent. So Kb is called ebullioscopic constant, purely depends on the nature of solvent. It is independent of nature of solute. Okay, so this is a relation between delta Tb and molality. From graph we can derive it. Is it clear? Next we see a problem on this. You read the problem. A solution containing 2.44 into 10 power minus 3 kilograms of solute in 75 into 10 power minus 3 kilograms of water and boils at 373.413 Kelvin. Calculate the molar mass of solute, and Kb is given for water. It is 0.52 Kelvin kilogram mole inverse. Okay, so here we have to find out the molar mass of solute. Let us write the relation between delta Tb and Kb, or in the molality. So delta Tb is equal to Kb into molality. Now you introduce the term of molality here. What is the formula of molality? Small w into 1000 by capital M into W. This capital M, this belongs to, you see, this belongs to solute only, paid by molecular weight. Weight of solute divided by molecular weight of solute. Whereas this capital W represent molar mass of solvent. So delta Tb means what? Elevation of boiling point. How can you define that elevation of boiling point? It is the difference between the vapor pressure of solution and vapor pressure of solvent. The difference between vapor pressure of solution minus vapor pressure of solvent. What is the vapor pressure of a solution given? It is given as 373.413 Kelvin. Solution minus solvent. So the boiling point of water is 100 degrees centigrade. 100 plus 273. We know that is 373 Kelvin. It is not there in the problem, but the boiling point, boiled, it is taken. Boiled at 373.413. All of you know the boiling point of water. How much it is? 100 degree centigrade. And it boils at 100 plus 273 means 373 Kelvin. That we are substituting. Is equal to Kb is 0.052 Kelvin kilogram mole inverse. And small w, what weight of solute is dissolved? 2.44 into 10 power minus 3 into 1000 divided by capital M. Capital M is here it is molecular weight of solute. Please, molecular weight of solute. So that we have to find out. Find the molar mass of solute. That is a question. Into capital W is the weight of solvent. What is the weight of solvent given? 75 into 10 power minus 3. So every term is known in this one. We have substituted for each and every one except molecular weight of solute. So you can write equation for molecular weight of solute, this one. Okay. So when you write equation for molecular weight of solute, it gives 2.44 into 10 power minus 3 into 1000 divided by 0.413 into 75 into 10 power minus 3. This also into 0. You remember it is 0.52. That you have to write it is 0.52. Here the multiplication should be there 0.052. So we get answer 40.96 into 10 power minus 3 kilogram mole inverse. This answer is 40.96 into 10 power minus 3 kilogram mole inverse. So here is a missing and 0.052 must be there. It should be multiplied with that. So on multiplication we can get this 40.96 into 10 power minus 3 kilogram. Like this we can solve the problem. Direct problems, all these are. Only one term is missing. Everything is given in the problem. The boiling point of water we have to substitute. It is not there in the problem. It is 373 Kelvin. Right? Okay. Next we see the second problem. Calculate Kb of water. Its latent heat of evaporation is 2260 joule per gram. So here 2260 joule per gram is given. Per gram it is given. But if you see the formula of Kb, because it is asked to calculate Kb, let you write equation for Kb, RT square into capital M divided by delta H vaporization. R is universal gas constant 8.314 joule mole inverse and Kelvin inverse. SI units we are substituting. T is nothing but the boiling point of water 373 Kelvin. You cannot substitute in degree centigrade, only you have to substitute in Kelvin scale. Okay. Next it is M1 is given. M1 is nothing but the molecular mass of water. How much it is? 18 grams, but you have to write in kilograms. We are substituting in SI units. That's why 18 by 1000, 0.018 kilograms. Delta H of vaporization. What is delta H of vaporization? 2260 per gram it is given. But you have to substitute in mole inverse. For 1 gram of water it is given as 2260 joules. But you have to substitute for mole. Mole means how many grams of water? 1 mole of water is nothing but 1 molecular weight. It is 18. That's why if you multiply this with 18, it will give the value for 1 mole. So 2260 into 18 joule mole inverse. Everything we are substituting. You see Kb is equal to R 8.314 T square 373 square. Capital M1 is 0.018 kilograms. Delta H vaporization is this one. You have to calculate for 1 mole. Actually given value 2260 joules is for 1 gram, but you have to substitute for 1 mole. That's why you are multiplying with 80. So on simplification we get 0.512 Kelvin kilogram mole inverse. It is ebullioscopic constant. Its value for water in this problem is 0.512 Kelvin kilogram mole inverse. Like this, the Kb purely depends on the nature of solvent. Here you cannot see any term which belongs to solute. Only solvent terms you can see in this is it. Okay, this is right. So like this we have solved some problems on elevation of boiling point. Third problem is also there. You can see here. A stone boils at 56.38 degrees centigrade. Is it? In pure state it is boiling at 56.38 degrees centigrade, and a solution of 1.41 grams of an organic solid in 20 grams of a stone. It is solution. How the solution is prepared? By dissolving 1.41 grams of an organic solid in 20 grams of acetone. The solution is prepared. This solution boils at 56.88 degrees centigrade. If Kb of acetone is 1.67 Kelvin kilogram mole inverse, okay, Kb is provided. Calculate the mass of 1 mole of organic solid. What is the meaning of calculate the mass of 1 mole of organic solid? Nothing but molecular weight. Every term is given except the molecular mass of solute. So, as usual, we consider the formula delta T B is equal to Kb into molality. Okay, delta Tb is equal to Kb into molality. Kb into molality term, we are introducing the formula of molality, weight into 1000 divided by capital M into capital W. Capital M, small w is the mass of solute, capital W is the mass of solvent, M is representing mass of solute. That is molecular mass of solute, not molecular mass of solute. So you substitute everything. What is delta Tb? Elevation of boiling point. Again, the difference between the boiling point of solution and boiling point of solvent. So boiling point of solution. The solution boils at 56.88 degrees centigrade minus 56.38. It is the boiling point of pure acetone. That is called Kb is given 1.67 into 1.41 grams of solute is dissolved. 1.41 we are substituting instead of small w into 1000 divided by capital M. Capital M is the molar mass of the solute you have to find out. And 20 is the mass of solvent, acetone. Here acetone, 20 grams. So this is 0.5 is it? Difference of this is 0.5. So you write equation for capital M. It is 1.67 into 1.4 into 1000 by 0.50 into 20. It gives 235.47 gram mole inverse. It is the molecular mass or the mass of 1 mole organic solid. Like this we can calculate that we can find the molecular mass of the solutes. Right. We have discussed about the elevation of boiling points and problems also. Now we see the fourth colligative property, that is depression of freezing point. What is the meaning of depression of freezing point? So the freezing point, the depression of freezing point is the difference between the freezing point of a pure solvent and the freezing point of solution. Remember, the freezing point of the solvent will be greater than the freezing point of solution. Means when a non-volatile solute is dissolved in a solvent, its freezing point decreases. That's why we say depression means decrease. Depression of freezing point means decreasing in freezing point. Okay, so how the situation, how the system will be present at freezing point, that we have to say. At freezing point of the liquid, what happened? Liquid equilibrium. Freezing point of liquid, equilibrium exists between the solid and liquid phases. What happened? The equilibrium will exist between solid and liquid phase. Suppose water is there. What is freezing point? Freezing point is 0 degree centigrade. At 0 degree centigrade, ice and liquid water will exist in equilibrium. Means here water will gradually converts into ice and ice will gradually converts into water. Both the forward and backward reaction takes place. All of these two processes, forward and backward, will exist in equilibrium. The rate of conversion of ice into water and the rate of conversion of water, liquid water into ice will be same. That's we say equilibrium. It is a dynamic equilibrium, we know that. So under this condition, see, the vapor pressure of both the solid and liquid will be equal. What was the condition in boiling point? At boiling point, what was the condition? The condition is the vapor pressure. That is, the condition is what? The liquid and vapor will exist in equilibrium. Here, at the depression, at the freezing point, how the equilibrium will exist? The equilibrium is existing between the solid phase and liquid phase. So that the vapor pressure of solid and liquid phases will be equal at equilibrium. Okay, when you dissolve a non-volatile solute in the solvent, what happened to vapor pressure? Vapor pressure decreases. When vapor pressure decreases, we know that the vapor pressure is a function of temperature, so that freezing point also decreases. That is the reason why the freezing point decreases. The freezing point decreases due to decrease in its vapor pressure, because the vapor pressure is a function of temperature. Both of them are directly proportional. And also we can see this reason. The chemical potential or escaping tendencies of solid and liquid phases will be equal at freezing point. So at freezing point, liquid and solid will exist in equilibrium. That is the first point. The second one is the chemical potential, let us say, or escaping tendency from one phase to another phase of solid and liquid will be equal. So the liquid solvent and solid solvent will exist in equilibrium. You remember, when a liquid is converting into solid in forward process, delta H will be negative. When a liquid solvent is converting into solid solvent, means the liquid is converting into solidification. This is exothermic. Exothermic. That's why delta H is negative. Means forward process is exothermic, whereas the backward process is automatically endothermic. It will be the endothermic. So the forward process is exothermic. This is the exothermic. Whereas the backward process is endothermic. Conversion of solid into, is it liquid? That is endothermic. So when a non-volatile solid is added to the liquid, what happens? The solvent, liquid solvent, the escaping tendency of solvent molecules from liquid to solid decreases. Due to addition of non-volatile solid, what happens? The escaping tendency of solvent from solvent, liquid solvent to solid will decreases. Means the amount, the rate of forward reaction will decrease here. The rate of forward reaction will decreases here. Why it is decreasing? Due to addition of non-volatile solute to this liquid solvent. When you are adding a non-volatile solute to this liquid solvent, what happened? The forward reaction, the rate of forward reaction decreases. Means conversion of liquid into solid will decreases. Whereas the addition of non-volatile solute to the solvent will not affect the backward process. It will not affect the backward process. Is it? It is remains unaffected. So only the forward process is affecting. How it is affecting? The forward process, the rate of forward reaction is decreasing. Is it so? The rate of forward reaction is decreasing. When the rate of forward reaction is decreasing, means a less amount of heat will releases now. Because the rate of forward reaction decreases, so the less amount of heat will release. When the less amount of heat releases, what happens? The temperature remains, but also decreases. So when a non-volatile solute is dissolved in the liquid solvent, at equilibrium, suppose at equilibrium, if you are dissolving a non-volatile solute to the liquid solvent, then what happens? The rate of forward reaction, that is conversion of liquid into solid, will decrease. Means less amount of heat will decrease. So that what happened? The temperature of the system will decrease. So that a new concentration again, and a new concentration again, the chemical potentials of liquid and then solid becomes, solid solvent becomes equal. Again, it will retain the equal chemical potential when the equilibrium existed. So in two ways you can understand this concept. We know that P naught is greater than P. Vapor pressure of solvent is greater than vapor pressure of solution. When you dissolve a non-volatile solute into solvent, the vapor pressure decreases. The vapor pressure is a function of temperature. That's why the freezing point decreases. This is one of the reasons we can give. What is the second one actually? When you are dissolving a non-volatile solute in the liquid solvent at equilibrium. So what is the equilibrium? The equilibrium means here the liquid and solid are existing in equilibrium. Under that condition, you are adding non-volatile solute. Then what happened? The rate of conversion of liquid into solid will decreases. Here you see in this equation, this exothermic rate of exothermic reaction decreases. The speed of this reaction decreases. So that what happened? The less amount of heat will release in the system. So temperature will fall. Again, system will establish the equilibrium. Again, then what happened then? In next new state, the chemical potentials of both liquid and solids will becomes equal. So like this, why the freezing point of a solution is less than the freezing point of solvent, that we can explain beautifully in this is it. So P naught is greater than P and T naught is greater than T. T naught means the freezing point of the solvent. T is the freezing point of the solution. Freezing point of solvent is greater than freezing point of solution. So the difference between these two, T naught minus T, is called depression in freezing point, represented by delta TF. Represented by delta TF. This is the concept. So in this graph, you can show the concept of depression in freezing point. This graph is drawn between vapor pressure versus temperature. This is a liquid solvent. As the temperature increases, vapor pressure increases. This is given for the solution. Means solvent plus non-volatile solute. The vapor pressure of solution is less than the solvent. Clearly, we can observe this. Is it? So here you can also observe this one. The vapor pressure of liquid solvent is P naught at this temperature, at this TF temperature you are observing, and the vapor pressure of solution is, let's say it is P, which is greater, P naught is greater than P. Next, you can also see the freezing point. This is a solid curve. It is frozen solvent solid curve. So as the temperature of the liquid solvent gradually decreases. Now at this point what happened? Both the solidification will start and both the solid and liquid will exist in equilibrium. This is called the freezing point of solvent. Next, in the case of solution, when we freeze the solution, when we cool the solution, gradually we are decreasing the temperature like this. Here solidification will start and solid and liquid will exist equilibrium. That's why T1 or TF or T1, let's say here T1 is the freezing point of the solution. So the difference between the T naught F and TF is called this difference. It is called delta TF. That is depression of freezing point. This is depression of freezing point. So we can show the graphically, very easy. What depression of freezing point. Let me discuss the derivation of the relationship between the depression of freezing point and molality of solution or the molecular weight of solute. Let me see the thermodynamic derivation. So the freezing point of the solvent decreases when a non-volatile solute is dissolved in it. We know that, is it? So at equilibrium, which will exist in equilibrium? Liquid and solid are existing in equilibrium, and at this equilibrium, the chemical potential of liquid will be exactly equal to the chemical potential of solid. Chemical potential of liquid is exactly equal to chemical potential of solid. So now we are writing for, in case of liquid, you are writing mu1 L is equal to, L means L1 is the liquid phase, mu1 always given for solvent, mu2 means it will be the solute. Chemical potential of solute mu2, where chemical potential of solvent is represented by mu1. So mu1 in liquid phase is equal to mu1 mu naught 1 plus RT log x1. This is a relationship between the liquid chemical potential in the solution and liquid chemical potential of a liquid and its mole fraction in the solution. This equation explains what? Relationship between the chemical potential of solvent and its mole fraction in the solution. Okay, so now we are adding to the solvent. What we are adding? You see, non-volatile solute is added. So when a pure solvent is there, x1 is equal to 1. When we are adding the solute to it, what happened? X1 will decreases. Means the mole fraction of solvent gradually decreases. When you are adding the solute, what happened? The mole fraction of solvent gradually decreases. So under this condition, we can see the change in, when we are adding a non-volatile solute to prepare the solution and equilibrium is established, and under that equilibrium, a small change in chemical potential of liquid phase will be exactly equal to small change in chemical potential of solid phase. That is, change in chemical potential of liquid will be exactly equal to change in chemical potential of solid. Okay, this we have to see. Now we have to calculate for this. But already we have discussed in the case of elevation of boiling point that in liquid phase solvent in the solution, the chemical potential is a function of temperature, pressure, and its mole fraction. Whereas in the pure solid state, when a solvent is existing in the pure solid state, we say mu1 S is equal to the chemical potential of a solid is a function of temperature and pressure. This is equation number 25. So let's consider this liquid phase only. What is the liquid phase? mu1 L is equal to, it is a function of temperature, pressure, and mole fraction. Now we differentiate this with respect to what you calculate the differential value of this one, change in chemical potential of solvent, so that we will perform what partial differentiation with respect to each and every term by keeping the remaining uh, variables constant. If you see, you differentiate this one, d mu1 L is equal to, now p and x1 are kept constant, you are differentiating with respect to t, so dou mu1 L divided by dou t into dt plus again you differentiate with respect to p, so that t and x1 are kept constant, you can see here. So what we are writing, you see, dou mu1 L divided by dou p into dp plus, again you differentiate with respect to x1, so that t and p will kept constant, so dou mu1 L divided by dou x1, it constant temperature and pressure into dx1. So this is the equation we got. We are calculating the small change in the chemical potential of liquid. The chemical potential of liquid in the solution is a function of temperature, pressure, and its mole fraction. Each time we are differentiating with respect to one term, variable, and remaining variables are kept constant. That we are doing here, right? Next, you see this d mu1 L is equal to, whereas this first term represents d mu1 divided by dou t, dou mu1 divided by dou t at constant pressure and temperature. This is nothing but minus S. Actually, it is partial molar entropy, whereas d mu1 divided by dou mu1 divided by dou p at constant temperature and x1 is, it is v1 partial molar volume it represents. But instead of partial values, finally we will equate the partial molar entropies and partial molar volumes to the molar entropy and molar volume. That's why directly we are considering the entropy and volume terms as it is here, not the partial terms. We can also use the partial terms. So d mu1 L is equal to minus S1 bar, or means partial molar entropy L dt into V1 bar partial molar volume into dp into dou mu1 divided by dou x1, dou mu1 L divided by dou x1 into p into t at constant pressure and temperature into dx1. d mu1 L is equal to minus S1 bar L dt plus V1 bar L dp plus dou mu1 L divided by dou x1 at constant pressure and temperature into dx1. But at constant pressure, this becomes 0 because dp becomes 0. Only these two remaining terms will be written here. In 26 equation, you can see only these first and last terms are there. The middle term is vanished out because dp is 0 at constant pressure. So we have to derive this equation, this value. We have to evaluate for this value. For that, we are writing this mu1 L is equal to mu0 1 L plus RT log x1. So in order to get this one, you differentiate with respect to d by dx1. So d mu1 by dx1 at constant pressure and temperature, that is equal to, whereas this is a constant, it becomes 0. So RT by dx1 in d into log x1 in liquid phase. Means each and every term is multiplied by d by dx1. So this will become 0. So we get this equation. So instead of this, what we can substitute here? Instead of this equation, you can substitute, you see, instead of this part. Now we can substitute this one. So d mu1 L is equal to S1 L dt plus L means liquid phase. S1 is the molar entropy plus RT. What is d by dx1 of log x1? It is because here you see, when you substitute this one, this dx1 and dx1 will get cancelled. dx and dx get cancelled. What is the remaining part? RTD log x1 in liquid phase. So this is a change in chemical potential of liquid phase in solution. Okay. Next, similarly, we see for solid phase. What is solid phase? Its chemical potential of solid phase will be a function of what? Temperature and pressure. Change in chemical potential of a solid phase d mu1 s is equal to, you keep this pressure constant, that is dou mu1 s divided by dou t at constant pressure and mole fraction of solute dt, plus again you are differentiating, partial differentiation again with respect to dou p. So dou mu1 s divided by dou p at constant temperature and mole fraction of solute it into dp. No need to mention the mole fraction because the pure solute solvent is there, is excess or x1 and excess, both of them are. Excess means here the solvent mole fraction, x1 is the mole fraction of solvent. It is also mole fraction of solvent. So what is d mu1 s divided by dou t at constant? This is again molar entropy of the solid phase. Molar entropy of solid phase. Here dp is equal to constant. At constant pressure dp becomes 0, means this will be vanished out. Let me see in the next slide. Yes. Again we have carried as it is. So this becomes 0 because pressure is constant. So only the remaining part will be this one. Instead of this d mu1 dou mu1 divided by dou t at constant pressure and mole fraction of solvent into dt. Instead of this, what we can write? Minus s1 of solid phase into dt. So it is entropy of solvent in solid phase into dt. So this is obtained at constant pressure in the case of solvent. Is it? Is it? Next you see the previous slide. Here this is obtained in the case of solvent, whereas this is obtained in the case of solid phase, liquid phase and solid phase. So the change in chemical potentials of these liquid and solid phases will be same. That's why d mu1 liquid phase is equal to d mu1 solid phase. Change in chemical potential in the liquid phase of the solvent in solution is equal to change in chemical potential of the solvent in solid phase. So both of these equations we can equate and bring the entropy terms together. Just we are shifting this, is it? So S1L minus S1S, there is nothing but delta S fusion. What is delta S fusion? It is molar entropy change of fusion. Molar entropy of fusion. Molar entropy change of fusion into dt is equal to RTD log x1. But delta S is equal to delta H by T, we know. Delta S is equal to delta H by T. What is delta H fusion? It is molar enthalpy of fusion. T is the freezing point of that liquid. So delta S fusion, molar entropy of fusion is equal to molar enthalpy of fusion divided by its freezing point. Let me substitute there. So on substituting this, we are substituting this one. We get delta H fusion divided by T into dt is equal to RTD log x1. Okay, this is the equation we got. Right. Next, we will integrate this equation. Delta H fusion divided by T into dt is equal to RTD log x1. Or you bring temperature terms together, energy and temperature term together. So delta H fusion divided by T square. This T we are writing in this side. And R also we are shifting here. Delta H fusion divided by RT square into dt is equal to d log x1. Same thing we have mentioned here. These two equations are same. Now we are integrating this equation with these limits. What are the temperature limits from T to TF? Okay. Next, what are the limits of this mole fraction of solvent? It is 1 to x1. When the mole fraction is present in the pure state, its freezing point is represented by T. When the mole fraction of solvent reaches to x1, now the freezing point of the solvent is represented by TF. Within these limits we are integrating. So when you are integrating this one, the integration of this part, integral of 1 to x1 d log x1 is nothing but log x1. because the differentiating and integration will get cancelled. So log x1 is equal to integration of dt by t square is minus 1 by t. After applying the limits, we have minus delta H fusion by R into 1 by t tf minus 1 by t. Now you see the LCM. LCM is t into t off, so that we get t minus t off. So log x1 is equal to minus delta H fusion by R into delta tf by t into tf. Again, what we are saying, you see, log x1 is equal to log 1 minus x2, because x1 plus x2 is equal to 1, that is equal to minus x2. Okay, now we are substituting delta tf is equal to RT square by delta H fusion into x2. What is x2? Mole fraction of solute. What is the mole fraction of solute? In case of dilute solution, it is N2 by N1. So we are introducing that N2 by N1 as what? Weight and molecular weight terms. So W2 by M2 and W1 by M1. 2 number is given for solute and 1 is given for solvent. Next, delta TF is equal to RT square by delta H fusion into, we are introducing the molality. We know that X2 is equal to molality into M1 by 1 kg. So if you write the molality term, capital M1 into small m. So delta TF is equal to Kf into molality. This is a relationship between the preparation of freezing point and molality. This Kf is called as cryoscopic constant. What is Kf? Here you can see Kf is equal to delta Tf by molality. Kf is equal to delta Tf by molality. So if molality is equal to 1, we can write Kf is equal to delta Tf. So how can we define this Kf? Kf is defined as, it is a depression in freezing point of 1 mole solution. Depression in freezing point of 1 mole solution is called as cryoscopic constant or mole freezing point depression constant. Like this we can calculate. What is the equation for cryoscopic constant? Here you can see the equation for Kf is it, because which term is replaced as Kf? RT square by delta H fusion into M1 is replaced by Kf. So Kf is equal to RT square by delta H fusion into M1. Here also you can observe the Kf purely depends on the nature of solvent, not on the nature of solute. It's a relationship between the delta Tf and molality. You are derived based on the thermodynamic concept. So what we have discussed here, we have discussed the relationship between the elevation of boiling point and relative lowering of vapor pressure. Then we have seen some problems on elevation of boiling point. Then we have discussed about the freezing point, the condition prevailed at freezing point, what state exists at freezing point, why the freezing point of solvent decreases due to addition of non-volatile solute, that we have seen, and we have derived the relationship between depression of freezing point and the molecular weight of solute based on thermodynamics. Thank you.